Let's have a bit more formal look on histograms with a goal to define an optimal histogram for a certain error metric. So assume we have a set of n data points, like in the previous examples we had data points 1 to 20, and each data point has a certain frequency, denoted by f of Si. In short, we can also write Fi. What we assume further is that these values, these points, are sorted. So Si is smaller than Si plus 1. So we have a sequence here. If we take an array now, f, that contains the frequencies, so f of S1, f of S2, and so on, then this f is nothing else than, in the very first example on histograms, we looked at the distribution. We had like 1 happened 0 times, and then we had 2, I think was 6 times, and then we had 3 was 19 times, and so on. Remember this? This was not really a histogram. This was the pure and exact distribution of the frequencies for these 20 points. This is exactly what is f. And now a histogram, also already discussed previously, wants to make groups of these values. Let's say you want to group the first 5 values in one bucket, the next 5 values, and so on. And this is also the goal here. So histograms partitions this vector into b buckets. The vector corresponds to this plot, the unhistogram plot, let's say, right? This one histogram bar for each value. And we want to make now b buckets out of it. So b is the number of buckets. Each bucket, we also call this interval here, I, subscript I, is one of these buckets. And the number of buckets has to be or should be much smaller than an n, obviously, right? Because we want to reach some compression, some coarsening in order to not having to store too many values. Each of the intervals I is represented by the height of this interval, which is like the height of the cell, right? Of this histogram cell, if you're talking about these buckets. The value, the height hi, this can be the absolute frequency or the average value. So the average frequency, when we take the absolute frequency and we divide it by the width of the bucket. Each interval has a beginning and an end, denoted bi and ei. So that means it contains the following values: SBI, SBI plus 1, SBI plus 2, and so on, until SEI, the end of the interval. The frequencies of these values are approximated by the height of this histogram, hi. Yeah? And we're talking about the average frequency here for the hi. So now how frequent is the value SBI plus 2? Well, in principle, the true occurrence is denoted by f of SBI plus 2, so the frequency of SBI plus 2. Of course, once we did the histogram creation, we don't store these individual exact frequencies, but we approximate the frequency by the height of the, by this average value, the height of the histogram bucket. And this is exactly hi. Right? So obviously, in general, we do a mistake, so an estimation mistake. And this is usually considered to be, or measured to be, either the absolute error or the squared error, hi minus FBI plus 2 squared. For completeness, let's write down the equation for the average value, hi, for an interval. This is simply the sum of the frequencies divided by the width of the bucket, as I already mentioned earlier. And now we can specify a popular error metric, which is called the sum squared error, SSE. The SSE for a certain interval, the starting and ending value, is defined as the sum over the values inside this interval. So k is the value inside the interval, we sum up from A to B, and we take the real value of this the real frequency of this value, given the frequency vector from before, f, minus the average value, so the estimate, and we take this the square of this, right? So hence the name sum of the squared errors. This is like the squared error, and this is the sum, right? So if you do this for one interval, or multiple intervals, or for the entire space of values, then we can say that one histogram is better than another histogram if the sum squared error is better, so smaller, right? And we want to find the histogram, or want to create, using an algorithm, the optimal histogram according to sum squared error. That means that no other histogram can have a better or smaller SSE. The approach that we discussed now was published in a paper in '98. I can recommend to read it, at least the beginning parts, because it gives a nice overview of the problem as well, and in particular also the algorithms. But well, I think the slide should be enough, but if you want to have a look, I can only recommend that. It's always better to have a second point or a second way to get an explanation. So these histograms that I presented in this paper are called V-optimal histogram. And these are optimal regarding SSE. And let's have a look how the algorithm proceeds. The algorithm works over a structure called SSE star. This SSE star denotes the smallest sum squared error of a histogram that considers the first I values of our data and is using K buckets. So we will see the algorithm later on how to compute this, the best or the minimum sum squared error. But this is important to remember now. SSE star is the smallest SSE achievable by a histogram, looking at the first I values and using K buckets. Okay, now it's getting, this is like the most important part. How do you define this? Because then the algorithms follows quite naturally out of this. So the SSE star I, K, so the first I values and K buckets, is defined as the minimum over, parenthesis opening and closing, the following. We iterate over parameter I, and SSE I and K is the minimum over all possible SSE stars of J, K minus 1, plus the SSE of one additional bucket. Now this is of course difficult to understand and difficult to explain. Let's draw something. So we have data here and we look at the first I data points, right? So 1, 2, 3, 4, 5 until I. And this one here should be the minimum sum squared error for a histogram over these first I points using K buckets. And this we find out by trying out all possible J's, for instance here, and then the SSE IK would be the SSE using the first J values only, and K minus 1 buckets plus one more bucket. And this is exactly this one more bucket, or more precisely, it's the sum squared error of this additional last bucket. And this one here, by definition, is the smallest sum squared error for a histogram looking at the first I values and using K minus 1. And then one additional bucket. In total, we have here K minus 1 buckets Here we have one more bucket, so in total we have k buckets, and this is exactly the k we want to compute here. Right. Note that this one here is the sum squared error. It's not the sum squared error star, so this is the pure sum squared error of this very last bucket. So now we do this again. We try a different j, let's say a larger one. Same thing. What is the sum squared error now? It's the best sum squared error of a histogram for the first j values with k buckets plus one more bucket. And we do this for all possible j's. We iterate. For each of these j's, we're getting one value according to this part of the equation. And then the minimum value will be taken as the sum squared error star, so the cheapest or the smallest sum squared error for the first I, and using k buckets. And the algorithm later on will start with small values or initial values of I and k and build larger and larger histograms by considering more and more initial values and more buckets until we have reached our goal of b buckets and the all the values that we have. So this computation makes use of the following fact. So if we have the SSE of an interval ij, this is smaller, this is bigger or equal than the SSE of the interval ik plus the SSE of the interval k plus 1j. And important here, apologies for the use of the same parameter twice, this k is not the same as this k. Here k is a data value, so this is denoting here the end of the interval or the beginning of the interval. So why is this true? What does it mean? So if you have a range, an interval from I to j, what this says is basically that the sum squared error of this, if we have an histogram, the sum squared error of this histogram is bigger or equal than if we would give ourselves one more bucket. In this case, exactly here, for instance, this means that if we have a histogram now consisting of this bucket, and let's say this bucket, then the sum squared error of the blue one is smaller than the sum squared error of this one plus the sum squared error of this one. Okay, why is it so obvious that this is true? What does this mean? It just means that if you have a data range, ij, and if you separate or partition this data range into two buckets, not only in one bucket, then the individual or the sum of the individual sum squared errors is smaller than the sum squared error over the big range with one bucket only. This means that if you have more buckets available, the sum squared error will not get worse. And this should be very intuitive to all of you, I hope. So again, we have the instruction how to compute SSE star of I values and k buckets. It was exactly what we have already seen earlier. And here is the idea, but I have already explained this on the previous slide. So the computation of SSE star is based on formal solutions, because you're incrementally creating more and more solutions for the best possible SSE for these parameters I and k. And here we see I and k, and SSE star of I and k is based on previously computed smaller solutions. So j is smaller than I, and k minus 1 is obviously also smaller than k. So we will start with small parameters I and k, and incrementally build up more and more knowledge about the best possible SSE until we have reached our goal of having B buckets and our entire data set. And here's the solution or the algorithm that is doing the computation. You see here the way the parameters grow. And of course, K goes from 1 to B. B is the number of buckets we want to invest in our histogram. I is the number of data points to consider, from 1 to n, obviously. And now this inner part here, the for loop for j is 1 to I, this is exactly this one here, right? And then here, if we denote by an array, how you would implement that by an array, a two-dimensional array, because of the two parameters here, we have a two-dimensional array. And what you're doing in this if statement is to just update the best solution for j data points and k minus 1 buckets. This is only the implementation to find the minimum, which is nicely expressed in mathematical way here in this one line, right? So this corresponds to this. This here is this here. And the update is exactly what you're doing here. I mean, the entire equation, or the minimum computation. So again, the essence of the algorithm is the definition and the understanding of this SSE star computation. And the algorithm you see here, which is dynamic programming, obviously, because of the storing of previous best solution and constructing optimal larger solutions. This is only a consequence of the definition of SSE star. What is not shown here is that you have to keep track when you're finding these best errors. Yeah, for each of these iterations, for I and K, you have to also remember what was the best choice, what was the best J, in order to really specify the histogram in the end, because the algorithm here would only give you the best SSE star, but would not tell you right away, so explicitly it would tell you what are the boundaries that you have decided. It's also important to note that this algorithm is not creating equi-depth or equi-width histograms. Here the intervals can be arbitrarily wide. They don't have to be the same width and also not the same depth. If you're looking at the paper, and we will have probably a small exercise on that as well, there's one lemma which is giving you a little trick on how to implement this efficiently, because you don't want to implement SSE computation so that this is dominating the runtime of the algorithm. But luckily they found out ways to pre-compute certain arrays, which are given here. With the use of these, you can compute the SSE much more efficiently. Let's have a look for some sample data. So we have B is 5 and 4. So in one case we have 4, B is 4, and B is 5. And the different colors here, they denote the boundaries or the individual buckets. So for B is 4, the optimal histogram regarding SSE consists of the first 3 values, the next one, the next 3 values, and then we have a wider range, and then the final bucket. So you see these buckets don't have an equal width. Yeah? And if we have one more cell, like one more storage space that we want to invest, so B is 5, then you see the solution, the range is here. So these V-optimal histograms are the optimal histograms regarding to sum squared error for a given user-defined number of buckets you want to invest, so you want to tolerate, because this also requires, of course, storage. Then if you say I have my data and I want to have 100 buckets, then this algorithm will give you the best bucket boundaries which minimize the sum squared error. That's the idea behind that.